Hey everybody, welcome back to another AP Physics video. Today I'm going to be discussing circuits, and we're going to be creating 3 different circuits where we include different organizations of resistors and even capacitors to better understand how voltages behave, how current behaves, and things like that. So let's dive into it. So let's start with a simple series circuit. So I've got a battery connected to 3 resistors, one after another, which is a series connection, and everything shares one single path, so the current is the same everywhere. Now, to understand how voltages behave, we're going to use Kirchhoff's loop rule, and the loop rule says that the sum of all voltages rises and drops around any closed path must add up to 0. So in this circuit, let's pretend this battery provides us with plus 9 volts. So as current flows through each resistor, there are voltage drops, and when we add up those drops, they must equal to the battery's 9 volts. So if I take a voltmeter over here, we can measure this resistor to have 3 volts, and finally 3 volts. Those 3 resistors each have 3 volts, which add up to 9 total volts. So obviously all of these resistors have the same resistance, but in general, the smaller the resistor, it gets a smaller drop, and the bigger the resistor, it gets a bigger drop. And the total should add up to 9 volts every time, no matter what happens in this circuit. And that's the loop rule in action. So since all resistors are in series, the total resistance is just the sum. And the current is just I equals V battery times resistance total. So essentially, in series circuits, there's the same current, voltage divides, resistances add, and the loop rule keeps everything consistent. So now just a quick thing, let's see what happens when we add a light bulb at this point on the resistor, or the circuit. So obviously we can see that the light bulb acts as a resistor as well, but since current is continuously flowing, the light bulb is staying at the same brightness. So just so you guys can visualize it, current is continuously flowing, light bulb is staying the same, but it also acts as a resistor. So we can see that 4.5, a total of 4.5 volts plus 2.25 plus another 2.25 equals 9 total volts in the battery. As you can see, there's a total of 9 volts, and all of this should equal 9 volts. There we go. So again, the light bulb also acts as a resistor. So now we're going to look at parallel resistors, which behave very differently from resistors in series. And we can see that the wire split into 2 different branches, so the current has more than one path to choose from. And the moment the current splits, we will use Kirchhoff's junction rule to determine what the current, like the behavior of the current, what it looks like. And the total current entering the junction equals to the total current leaving it. So the total current entering over here must equal the total current exiting over here. So essentially, if 1 amp is flowing into these resistors, 1 amp has to flow out, and that can be done in any sort of way where the top resistor can receive 0.7 amps, or the bottom resistor receives 0.3, or it can be split evenly if the resistances are the same. But essentially, the way in which the amount of current splits between these 2 paths depends on the resistance. Obviously, the current will want to go down the easier path. So yeah, the big picture is that in parallel circuits, there's the same voltage in this loop, in this little loop over here. The total voltage over here minus the total voltage over here has to equal 0. And the currents split at these junctions, and the junction rule ensures that they add up correctly. So finally, let's explore a circuit with a capacitor, which brings in a time-dependent behavior, and over here we can see that we have a classic RC charging circuit, and this is where we have a battery, a switch, a resistor, and a capacitor all in series. So the instant I close the switch, the capacitor will remain uncharged, which means that its voltage is 0 volts, and essentially due to the loop rule, the current will be at its maximum possible value, which is why the ammeter spikes immediately. So as you can see, the switch is closed, and the ammeter is reading its highest amount of amperes. So let's see what happens when I start the simulation when the switch is closed. We can see that charge quickly accumulates on the capacitor's plates while current is decreasing exponentially. So this is essentially what we saw in class when we were drawing those graphs. The voltage on the charge on the plates of the capacitor as time passed, and the current as time passed, where the charge on the plates of the capacitor increased exponentially while the current decreased exponentially, exponential decay, asymptotic to zero. But as time passes, again, charge accumulates on the capacitor's voltage increases, and current decreases. And essentially, due to the loop rule, voltage across the resistor decreases, voltage across the capacitor increases, and the current drops over time. And after a long time, after the switch is closed, essentially after an infinite amount of time passes, the current will eventually reach zero. But in reality, this typically won't happen. Eventually the capacitor's voltage becomes equal to the battery voltage, so no current flows, and the capacitor behaves like an open circuit, a break in the wire. The resistor has zero voltage across it, and the circuit is effectively off, even though the switch is closed. Now let's take a look what happens if we add a light bulb. Let's see what happens to the light bulb in this RC circuit. And essentially, the light bulb is just another resistor. We can see that immediately after the switch is closed, the current is 1 ampere. There's no charge on the capacitor's plates. But when we play this, the light bulb quickly dims. And this is, again, due to everything I just said, where current slows down, charge on the plates accumulate, and this essentially will happen in a matter of nanoseconds in the real world, where you probably won't even see the light bulb being on in the first place. That's how fast this process takes. But yeah, that's basically it for these 3 circuits. And next in the video, I'm going to show you guys how to solve a circuit puzzle. So here we have a circuit puzzle where we're going to use everything we learned in this unit to fill in all of these unknown values, where we'll also include the loop rule and junction rule. This link can be found in any of Mr. Flaherty's Google Classrooms, I'm pretty sure. I'm not sure about the other physics teachers, but you can also go to the link shown at the top of my screen. So let's first fill in all of the directionals, since we know the direction in which current is flowing, out of the positive side into the negative side. So let's fill all of that in. And now let's try to fill in some of the easy stuff. So we know that we have a 2 ohm resistor over here, 10 divided by 5 equals 2, where we also have 8 amperes, so a total of 8 amperes of current in here, which means we need to have 8 amperes going into there. That is the junction rule. And we also need to know that 8 minus 2 equals 6, which means we also have 6 amperes of current flowing through these 2 resistors. Again, the junction rule, which ultimately means we have 8 amperes flowing into this whole entire system of parallel and series resistors. So this is 6 volts over here, 6 volts. We have 12 volts over here, and we need to have a difference of 0, which means there's 18 volts down here. 6 plus 12 equals 18. 18 minus 18 equals 0 in this loop over here, which means that this is a 9 ohm resistor, and this is a 2 ohm resistor. So this whole entire loop over here is complete. Let's move on to this next one. Let's see if we can figure out anything over here. We know that there's 8 amperes of current flowing out of this system. Again, the junction rule, 8 amperes flowing in, 8 amperes flowing out. And we also know that there's going to be 3 amperes flowing through these 2 resistors in series. As we can see, 3 amperes over here, 3 amperes out, where this is going to be an 18 volts over here. Moving on, we also know that there's going to be 5 amperes of current flowing through here. Since these resistors are in series, which means that this is going to be 5 volts, and we need to make sure that the total voltage, the potential difference, is going to be 0. So this is going to be 15 volts up here and 5 ohm resistor. So we know that the total voltage of this whole entire top section over here is going to be 18 plus 15, which is essentially 23 or 33. So the whole entire voltage or potential difference of this circuit is going to be the top, this V over here, and this V over here. 33 minus 33 equals 0. So we know that this whole entire loop now has a potential difference of 0. And this is essentially what we did over here. The potential difference is 0. 6 plus 12 equals 18. 18 minus 18 equals 0. 5 plus 10 equals 15. 15 minus 15 equals 0. And then for the whole entire circuit, it's 33 minus 33 equals 0. And we know over here that this is also another smaller loop. We're going to do the exact same thing. 33 minus 18 equals 15. This is 15 volts over here. So 15 plus 18 is 33. 33 minus 33 equals 0. So we also have the delta V equals 0 over here. And now we just finish this up. This is going to be a 5 ohm resistor, and we have 8 amperes flowing through this top half. We have 3 amperes flowing through this bottom half, which means we have a total of 11 amperes. And there we go. We have successfully solved this circuit. It's pretty straightforward. It's just a really fun puzzle. I would say. I think it was pretty fun to solve this. So yeah, we just used the loop rule, junction rule, even though I may not have strictly said it. Hey, we're using the loop rule, junction rule over here. I tried my best. I really hope this made sense. And again, you can find more of these practice problems at this link, or if you have Mr. Flaherty, it's posted in the classroom. So thank you so much. Good luck on the upcoming assessment, and maybe in the next AP Physics video we might have a special guest, just another student from our grade who is interested in taking part in the videos. So thank you so much again. Subscribe, and don't forget to advertise my YouTube channel to anybody else who might be enrolled in some of the courses that I tutor in. Yeah. So now I have to get back to studying. Thank you guys so much.